Example 9a, sketch the graphs. The function equals 2x plus 3.5, so that's the function f, and the function g is 0.5x plus 7. You can use technology to draw the graphs. You might need to change the level of zoom. Okay, you can see we've got the range from minus 10 to 10 and the domain from minus 10 to 10. So you could set your calculator on that in advance. And you'll find since these lines are not parallel, we know they're not parallel because they have a different slope. If that was a 2 and that was a 2, they'd be parallel and they wouldn't intersect. But these do intersect because they're not parallel and they intersect right there. Now we could just use the graph to find that point and hence find the intersection point, right? So that's B. The method is technology can be used to find the intersection point graphically. So just use analyze graph and use the intersection function and you'll find this point 2.33 for x and 8.17 for the functions, or for the y-axis there. So that'd be just 8.17. Looks good. Method 2, given that both are linear functions, you can solve simultaneous equations in two unknowns algebraically. All right, well, that's unnecessary, really, because at that point they have the same function value, so you just have to equate 2x plus 3.5 equals 0.5x plus 7 and solve for x. Once you find x, which should be 2.33, you put it back into either one of them and you'll find the y value, which is 8.17. Exercise 5F1, find the intersection point for each of the following pairs of functions. A, this function here, f function, and also the g function. Well, the intersection is where the function values are the same. In fact, where the x values are the same as well, but the function values are the same. So we can equate this function with that function. That's x minus 1, so we put x minus 1 on the left-hand side. That's 2x, so we put 2x on the right-hand side. We resolve it down to x equals minus 1. We then put that into either function. I've put them into both to show you we get the same answer. We put minus 1 into this function here, and we get minus 2. We put minus 1 into this function here, and we get minus 2. Therefore, the intersection point is minus 1, minus 2. B, this function f is 2x plus 3, and this function g is 1 minus 4x. They intersect where the function values have the same value, and again, the x have the same value as well, but the function values are the same. Therefore, 2x plus 3 on the left-hand side equals 1 minus 4x on the right-hand side. We resolve for x and we get minus 2 on 6, which is minus 1 on 3. We know x. We only have to put them into one function. Back here I put them into two to show you, but let's put it into just one function. I'll choose this function. I put the function, the f function, at the x value of minus 1 on 3 equals 7 on 3. So the intersection point is minus 1 on 3 and for x and 7 on 3 for y. And we can double check that we get the same function value when we put x equals minus 1 on 3 in the g function here, and we get 7 on 3 as we expected. So that's the intersection point. Question 2. The managers of a factory are trying to determine what to charge for an item they make. The demand for the item, a measure of how many are likely to sell, can be modeled by this function, where D is demand, the demand function of 800 minus 2p, where p is the selling price in dollars. The supply function can be modeled as supply function equals 3p. A, sketch both functions on the same set of axes. Okay, I've set that up here. This is p. This is the selling price in dollars. This is the number of items. And so the demand function is that one has a negative slope. As you could imagine, as the price increases, the demand for the item will be less. With regard to the supply function, as the price of the item increases, because there's a lot of money to be made with this item, there'll be more of them. So the supply will increase because there's a profit to be made. But how do we actually draw them? Well, let's have a look at the demand function first. This is of the form y equals mx plus b. That's the m, which is minus 2. B is 800. So we know that's the y-intercept. It crosses at 800. So we've got that point. Now we can see that it has a slope of minus 2. The gradient is minus 2. That means that it drops 2 for every one across. Now the problem that we have here is that we've got each line represents 100. So we've got 5. Each 2 of those represent 100. So it's very hard to see on this graph here a drop of 2 and a run of 1. So let's multiply the top by 100 and the bottom by 100. That would mean for a drop of 200, there'd be a run of 100. So that's 100, that's 200, and that's 100. So we could take that point there. And it's a straight line. We know it's a linear model, so we could just draw that and we'd extend it right through. That's how you draw that one. This one's a little bit easier, okay, because we know it starts with 0 because the y-intercept is 0. We saw that, right, in the previous practice. Okay, so if it passes through 0, 0, and it has a slope of 3, again, 3 is very hard to read here, isn't it? A rise of 3 and a run of 1. Why don't we change it to, we multiply the top and the bottom by 100, so that's 3 on 1 is the same as 300 on 100. So if we go up there, 1, 2, 300 is here, and we go across 100, and that's 100. That's how we got that second point. 2 points, it's a line, so we can just draw that line straight through there, and that will give us the intersection. Now, having said all that, I would suggest you just put in the calculator and use the analyze graph function, and you'll find the intersection. Probably a better way to go. B, find the equilibrium point for this item. The equilibrium point is where the supply and demand are equal, so we want to find that point. Well, again, if you'd put it straight in the graphic display calculator, you would find that point, and you could have already done this. Okay, there's 2 ways to do it without the calculator, and the first way is just by observation. Just have a look at it, and it looks like it's 100, and then it's 160. You go up there, you look across here, it looks like around 490, so that's what I guessed. But it's hard to interpret from the graph. More precisely, however, the equilibrium point can be found algebraically. It occurs where the functions equal each other. So we can take this part, 800 minus 2p, and put on the left-hand side, because that's the demand function, and the supply function was 3p, and then we just solve for p, and we find that p is 160, which we saw up here, so that was fairly accurate. All right. Then we put 160 into either equation. It'd be easier to put it in this one, but I've put it in this one here, okay? You could put in either one. I put in this one and I got 480. If you put in this one, you'll also get 480 because 3 times 160 is 480. So the point is 160, 480. That's accurate. This one was 160, 490. That was just through observation. If you put it through into the graphic display calculator, you would have got that answer there. C, comment on the situation in which the selling price is $100. Okay, so $100, so P is 100. So we use the demand function, and that's this one here. We put 800 minus 2 times 100, and that's 600. For the supply, we put 3 times 100, and that's 300. So therefore, the demand is double the supply. D, contrast your answer in part C to what happens when the price is 250. Well, we do exactly the same, but instead of 100, we put 250 in. So the demand function equals 300. The supply function equals 750. Therefore, supply is 2.5 times the demand. Question 3. Some friends are planning to rent a car during their holiday. They have 2 options. Option A is $5 per kilometre. Option B is a fixed cost of $150 plus $2.30 per kilometre. A. Find the cost of renting the car if they travel 100 kilometres under option A. Okay, so the cost for the option A was $5 a kilometre, so if it's 100 kilometres, that's 5 times 100 is 500. Option B is $150 plus $2.30 per kilometre, so that's 150 plus $2.30 times 100. That's 150 plus 230, and that's 380. B. Write down for each option an expression for the cost of renting the car in terms of the number of kilometres travelled, x. X is the number of kilometres, so the first function is our option A. We call that the A function. That's 5 times x, because x is the number of kilometres, and it's $5 a kilometre. Option B, that's our B function. That's $150 plus $2.30 times the distance travelled in kilometres. So that's 150 plus 2.3x. They know that above a certain number of kilometres, k, right, that's when x equals k, option A is more economical than option B. Find the value of k. K can be found by finding where the functions intercept each other. Okay, that's how we can find that. Also, I've put in the graphic display calculator, so if you put those both in, it's a lot easier than doing all these sums. So I'd put that straight in the calculator, use analyze graph, find that point, and that's the answer there. Now, they say option A is more economical than option B, but actually that's not the case. That's not the case. It looks like option B, after 55 kilometres, option B, because remember the vertical axis is actually the cost. So you can see as they cross over here, the red one is less than the blue one, and the red one is our option B. So option B is more economical than option A after the value of x equals k. And that's shown by this as well, obviously, because option B is at 380. That's cheaper than 500, and that's at 100k. Now, we found the value of k here when you equate the two functions, because that's actually what that point is. and you do it algebraically, you get 55.6, and the calculator showed the same. Then you put 55.6 into either of them, either of these two functions, and then you'll come up with the other number, 278, and that's what the calculator found. So this should be option B is more economical than option A there. And we've proved that down here, and it happens after x equals k, where k equals 55.6 kilometers. Question 4, consider the functions 2x plus 1 and mx plus 3, where m is a constant. The graphs of these functions intersect at a point -5 and -9. Find the value of m. Well, we know they're talking about the intersection point. If that's the intersection point, then these two functions equal each other at x equals -5, and in fact, at -9. So that would be -9 equals -9. But that's where they actually intersect, at x equals -5 and the function value of -9. So what we need to do then is equate the two functions and substitute x equals -5. The first function is 2x plus 1, so that's 2x plus 1 on the left. The other function is mx plus 3, so that's mx plus 3. And then we substitute x equals -5 because they told us that's where they intersect. So 2 times -5 plus 1 equals m times -5 plus 3. That's -10 plus 1 equals -5m plus 3. And that gives us m equals 12 on 5. B, find the point of intersection of the graph of x with the x-axis. Now, normally they would say the point of intersection of both lines, but that's not what they're saying here. They're saying, where does the g function cross the x-axis? Now, the x-axis is at y equals 0, or the function value of 0. That's the x-axis. So we just put the function value of 0 equals 12 on 5 times x plus 3, and we solve that, and we find that x is -5 on 4. Now, we already know enough. They just want to know the point of intersection. We know x is -5 on 4, and we know the function value is 0. So the point is -5 on 4 and 0. Now, what I did here is unnecessary, but it's a nice confirmation. If you put -5 on 4 back into this, that's -5 on 4 for that, as I've done here, then you should get 0, because we've already said this is happening at the function value of 0, or the x-axis.